There's going to be recommendations from field research on zero net energy apartments. Amy Dryden, Meg Mcduff, Emily Higbee. I'm going to give you a quick little bios on them. Amy Dryden is the Director of Strategic Innovations at the Association of Energy Affordability, specializing in strategic initiatives, codes and standards, program design and implementation, training and research and development projects. She's all of that. She brings more than 20 years of experience in residential green building design, construction, consulting, and planning, works to advance the industry to deliver sustainable and healthy housing. And Amy works with a diverse set of stakeholders, including contractors, consultants, building owners, developers, utilities, federal and state agencies, program managers, property managers, local governments. I mean, she does it all in service of building a decarbonized future. Meg Mcduff is a project manager at the Association for Energy Affordability with Amy. Meg provides technical analysis and project management services for the low-income weatherization program for multifamily housing. Additionally, she is currently working on 3 different CEC EPIC-funded research studies, all of which are researching and evaluating pathways to electrification and decarbonization of multifamily buildings, both in new construction and retrofit appliances. She's the project manager for one of AEA's newest EPIC grants, for which AEA is the prime, that is looking to design, fabricate, and test a packaged mechanical system product in the California multifamily retrofit market. And Emily is the Director of Research for Redwood Energy. Her current work includes being one of the lead authors on the Zero Emissions Single Family Retrofit Design Guide, as well as 4 other books that she's co-authored on how to electrify. She's a project manager at Redwood Energy on our CEC-funded EPIC grants, and our newest grant that we're starting on, she's leading, is load flexibility with heat pump water heaters. Okay, I'm going to stop screen sharing here. And could you all bring up your presentation? Welcome. Thank you so much. Oh, and before I start, I need for everyone to acknowledge Amanda. Woo! Amanda Hutchins is the organizer of this event.
Thanks, Amanda.
Yeah, Amanda. This is, I think, like her 4th one that she's organized. Everything is perfect. There's not a bit of it that isn't perfectly set up for me. All I gotta do is talk. She's amazingly competent, amazingly organized. Thank you, Amanda, for making this happen for all of us. Okay, thanks for that.
All right, thanks for that introduction, Sean. Very energetic. So yeah, we're going to talk about our lessons learned from our grant project that's been ongoing, and I'll be presenting with Amy and Meg. And I just wanted to give a shout out to the rest of the team, Andy, Greg, Sean, and Nehemiah. So just to give you a brief overview of what we're going to be talking about, Meg's going to present the project descriptions and our actual zero net energy performance. And then we're going to talk about some of the challenges and opportunities in meeting zero net energy. So that's from the consumption side, the production side, and from the modeling perspectives there. And just to give you some background information, this was a CEC grant, GFO 15308, starting in 2016 and will be ending soon in 2021. And this was 4 project sites in California. On the map there was Calistoga, Cloverdale, Sunnyvale, and Atascadero. The main goal of this grant was to assess the technical and economic potential of zero net energy multifamily construction with a focus on optimizing water heating performance. And a big part of this was also understanding how tenants use electricity, and all of this to inform best practices, codes, and standards. And here we are today, communicating our lessons learned. So just to talk about the data collection briefly, because it was a big part of this project, we did circuit and whole apartment consumption with the Nexi devices. That's that glowing green device there. It had in-unit real-time energy feedback to the tenants. We also collected the metadata like the occupancy and unit information. We performed energy models and took lots of photos and on-site observations. We also collected utility data from the owner and aggregated from the tenant. We monitored water flows, the pump power, domestic hot water tank flows and temperatures, took tenant surveys, took data on the outdoor air temperature and the in-unit temperature. And those are some pictures to go along with it, installing some of the equipment, the flow meter, and that bottom right is the inside the electrical panel and some of the monitoring equipment there. With that, I'll hand it off to Meg to talk about zero net energy performance.
Great. Thanks a lot, Emily. So I'm going to briefly talk through the 4 demonstration sites that Emily mentioned, and then I can give you a peek under the hood of how they actually performed. So you can go to the next slide, Emily. So Calistoga and Cloverdale, we've kind of lumped together. They're respectively located in Calistoga and Cloverdale up in Napa and Sonoma counties. Calistoga is a 48-unit multifamily building site with made up of 3 buildings, and Cloverdale is 32-unit multifamily building of just 1 building. And both properties have a central 3-in-1 combination system. It's a 4-pipe system that provides domestic hot water, heating, space heating, and cooling. And it's hooked up to hydronic fan coil units in each of the apartments. Both properties have rooftop and carport V&M PV systems, and are all 4 of these demonstration sites are designed to be Z&E. One quick thing on these 2 properties. So Calistoga is a little bit older than Cloverdale, and so was designed, constructed, and operating before Cloverdale was. And so lessons learned from Calistoga's mechanical system design and operation were used to inform the design at Cloverdale. Next slide. So starting with Calistoga, this graph represents the Z&E performance of the property. I've included 2 years here because I think it tells, there are sort of 2 stories to tell here. I want to focus on 2018, whereas the other properties I'm using 2019 data. But there were many changes made to the mechanical system at this property that really drastically changed the Z&E outcome. So all in all, the Calistoga family apartments did not meet Z&E over the course of a year. Each of the 3 buildings at the property had a common area meter and then individual tenant meters. So the 2 buildings without the AirMech system connected and the aggregation of all the tenants were all met net zero in 2018. And the 1 building, which the mechanical combination plant was connected to, did not meet net zero, and that really drove the kind of overall Z&E performance of the site. And then again, due to sort of optimizing or addressing system failures, changes were made to the mechanical system starting at the beginning of 2019 that really that resulted in kind of a drastic increase in energy consumption, and you can see that demonstrated in the whole building data here. So all in all, the site did not meet Z&E, but a lot of lessons learned came from this property to inform the next property at Cloverdale. Next slide. The property in Cloverdale family apartments did in fact meet Z&E starting in the 12-month period starting in February of 2019. So looking from February of 2019 to January of 2020, that 12-month calendar year did achieve Z&E. The reason we're looking at this time period instead of the 2019 calendar year is because there was a pretty major issue with the solar PV system that we caught with the monitoring data that I'm going to talk about a little bit later. But the performance of the property was still on track, and the performance of the PV system was something that really caught up with itself and was on track starting in 2019. So next slide. So the next property is down in Sunnyvale, Edwina Benner Plaza. It's a 66 unit, 3-building multifamily property in South Bay. They have a central heat pump water heating system that serves all of the units, and then each unit has a ductless mini split for space conditioning. And then the property has a NEM solar PV system that only serves the common area, so only offsets the common area load. And you can see here a couple pictures of the modular stand-in heat pump water heating central plant that I just mentioned, and it was sort of a first of its kind or cutting edge, and so it took a lot of design support from the project team to really optimize it on the design and operational side. Next slide. And from a Z&E perspective, we're only focusing on the common area as the solar PV system only offsets the common area meter. You can see here that the common area meter did not meet Z&E, though it got sort of within the realm. And with further optimization beyond 2019, there's sort of opportunity to get even closer. One thing that is particularly important to note, though, is that the common area meter actually met net zero operational costs. So the utility cost for the 2019 calendar year was actually a credit of $21 back to the property. And this property is served by PG&E, but is also on the local CCA. So those rates were really favorable for solar credits. Next slide. And last but not least is Atascadero. It's a 60-unit building down in Atascadero. It's called the Knolls at Avenida. This building has, this property has 2 multifamily buildings that each have individual systems. So they have unitary heat pump water heaters located up in a metal shed on the roof that we'll talk a little bit about later. And then they have ducted heat pump units for space conditioning located. The compressors are on the roof, and then obviously the air handlers are inside the units. And this property has a rooftop and carport VNEM PV system that serves the both common area buildings and the all of the tenants. Next slide. And then just taking a look at the Z&E performance of this property. This property also did not meet Z&E in the calendar year, in a single calendar year. Again, we're looking at the 2019 calendar year. And you can see sort of the breakdown between common area and tenant loads. If you look at common area loads and tenant loads separately, the tenant loads, aggregated tenant, did not meet Z&E, but it did get a little bit closer than the common area loads alone. So when you combine them, the common area load is sort of helping drive that positive consumption over the course of the year. And again, we'll talk about this a little bit later when we talk about VNEM allocation. But so overall, this is sort of the performance we saw after monitoring at these properties for 3 years and collecting utility data to look at, did the site meet Z&E as designed? Next slide, Emily. Thanks. And I'm going to pass it over to Amy to talk about some of the consumption side issues that sort of contribute to Z&E performance and whether a property or a building can meet the design Z&E goal.
Thanks, Meg. Good morning, folks. This is Amy Dryden. Nice to have you all here this morning. What we did, as Emily outlined earlier in our agenda, as we looked at kind of whether or not these projects met Z&E, we thought we would just take a little bit of a slice of each of them from the consumption side of what was not performing or resulting in higher consumption for some projects and what were some opportunities. Then Meg's going to go into the production as we think about PV from a number of different perspectives and how that informed or kind of affected their Z&E performance. And Emily's going to close us out with modeling and what the opportunities and or challenges were there. So I'm going to take you through the consumption. Next slide, Emily. Just a perspective for you, and is kind of looking at the end uses when we're thinking about net zero energy, right? You have to be thinking about what are kind of the priority end uses that we need to address in design or in efficiency of appliances, and kind of thinking about how do we achieve our goal. One thing to note, and I apologize for not putting this on the slide, in the central domestic hot water bars up above, you'll notice clearly that cooking, range hood cooking is missing from there. It was because of an issue with the circuit monitoring that we didn't have that specific load, but based on our data and experience, I would expect it to be right between MELs, right above the miscellaneous electric loads and lighting. So the top bar is central domestic hot water system. So we're looking at individual space heating being the highest load, then miscellaneous electric loads and lighting, one of our most challenging to address, compared to the individual domestic hot water down at the bottom, where obviously DHW is the highest. The outdoor condensing unit for the split heat pump system is second, and I'll talk about that, followed by miscellaneous loads and then cooking. So that just gives you a perspective of the kind of distribution of loads that we need to be looking at. Next slide. So what I want to do is talk about a couple of different conditions. These next several slides are about Atascadero. And so in that slide previously, when we were looking at kind of the second load, it was the condensing unit, which is our outdoor unit of the split heat pump system. And as we looked at this load, we noticed that it was a pretty high load. It was much larger than we expected that we saw through monitoring. And further digging into it, we realized there was a constant base load due to the operation of a crankcase heater. And so this was operating kind of 24/7 whenever there was not a call for heating or cooling. So that averaged about 3 kilowatt hours per apartment per day. And so if you aggregate that over the apartment complex, the whole development is over $6,500 for an unnecessary load. For those of you who don't know, the crankcase heater is really used to warm the compressor oil, so it doesn't mix with the refrigerant, kind of damage the compressor. So it's utilized for generally utilized for lower temperatures. And also you can have a delay in the compressor startup to allow that compressor oil to warm up to prevent that mixing if there's long durations of downtime of space conditioning operation. And this is not included on the specs, this use. It's also not included in SEER and EAR ratings. And if you go to the next slide, Emily, it's interesting just to see if we look at that 40-degree mark of when we want to see that in terms of colder operation. This histogram shows you our operation times. So it's it's like 10% of our operating time that this should be occurring, yet our total usage is actually about equivalent to our operational time of space conditioning. So we're actually in the process of looking to do some aftermarket kind of conditions to test some controls on the crankcase to see what that benefit is. But in terms of impacting, this load was a significant impact in preventing the tenant units from achieving Z&E that Meg was talking about before based on their allocation. That's one issue. Next slide. The next two things are all about location, location, location. And the left-hand picture there, should have put these in reverse. The left-hand picture there is showing you occupancy sensors in the kitchen and in the bathrooms there for the recirc pumps. And then the middle picture and the right-hand picture are showing you the location of the individual Rheem heat pump water heaters. They're up on the roof. You can see it on the left there before it gets framed in with all the metal siding panels. Needless to say, that was quite chilly in the winter in there. But these two kind of install locations had performance on both of these end uses. So I'm going to show you kind of what that looked like. Next slide. So this is showing you seasonal impacts. And I didn't put this on the slide, apologies. These are both from a heat pump set point and mode. Both of these are in 125-degree set point at energy saver mode. So on the left, you can see the winter daily. The right is a summer daily. Blue is a compressor, orange resistance there. And overall, we see increased resistance and compressor at kind of across the board for almost every apartment from winter to compared to summer. And part of it is because the location up on the roof, when we have colder temperatures in the winter, right? So we're going to require more energy to get that water up to temperature. But also we're seeing increased losses because of the location of the water going up to the roof. Also really decreased temperatures when that incoming water is being more impacted by those ambient, those overnight cold temperatures. And so these apartments have morning peaks, early morning peaks, like 5 a.m. Starting hot water peaks because of it's farm worker housing, and there's obviously earlier activity. And so we see a greater use of electric resistance in the winter in the mornings to overcome that. So yes, we know incoming water temperatures can impact performance of heat pump water heaters, but this particular condition kind of exacerbates it. The other thing I just want to note too, in terms of thinking about performance, is for these particular projects, we still see even in the summer that's more favorable. Probably 50% of the total usage is still resistance energy, and those are more favorable conditions, right? We'll have warm incoming water temperatures, and actually those metal boxes, sheds up there are nice and warm, so our ambient temperature is much warmer as well. Next slide. So the other kind of location issue I was sharing with you in that first slide was on the recirc controls. And so this was really fascinating, I think, just to see. On the left-hand side, you can see a plan of the apartment, and there's those orange dots and kind of, directional views. There was a infrared occupancy sensor to control the recirc pump in every single bathroom and in the kitchen. So what that meant is there was 3 different places, 2 to 3 places, depending on the number of bathrooms, in each apartment that was triggering the operation of the recirc. They were also installed, as they showed in the picture, kind of across from a mirror, which that reflectivity really affected kind of misoperation of these heat pumps, not heat pumps, recirc control pumps. And so the graph up at the top shows you the operation of the pump. In some cases, on average, it was like 100 times per apartment. In some cases, it went up to 300 times an apartment. So while this is not a huge amount of energy use in terms of pump energy, right, it did have an impact on the heat pump water heater performance, right? We're running water, we're pulling water off the tank through the recirc loop and bringing it back. It's warmer temperature, disrupting stratification. We're getting heat loss off the tank for no use. So the graph there kind of in the middle is showing you kind of the recirc pump energy, and then you can see right around in November where we replaced all the occupancy sensors with on demand. So you can see both a drop in DHW energy in terms of the heat pump water heater energy with the orange line, as well as the drop in recirc. So again, just pointing out, recirc can be challenging with heat pump water heaters in general. So look at what the manufacturer is recommending. But this is really to point out, we're going to make sure kind of the control strategies are positively effective for the system. And we would never have noticed this without monitoring. This also occurred in vacant apartments too, which kind of tipped us off to the reflective issue of the mirrors as well as just kind of multiple sensing. Okay. So those are kind of two big things that we called out in the Atascadero that had the individual systems. I want to talk briefly about central systems. So this is the Sunnyvale project Meg was talking about with the modular Sandin central heat pump water heater system. And so, you know, overall, we saw a well-performing system. If you look at the graph there in the bottom, the majority of the time, these systems were operating with COPs between 4 and 6, right? The highest percentage in those kind of buckets. But this would not have occurred if there was not kind of the significant technical assistance and oversight, verification in the field. First, there was challenges just in terms of right sizing straight out of the gate at the design phase, where we need to make sure we were prioritizing storage because we're moving from a gas system, right, to a heat pump system. And then also, what were we sizing for, and really identifying that the low medium demand was a good, was the right fit for multifamily. And so if we look at the EcoSizer system, that low medium demand was good. It kind of gave us enough coverage with not too much buffer, kind of a safety net in terms of sizing demand. But then when we looked at, we had some stuff kind of squared away and right on the design, but it was installed wrong. So on the recirc system, there was the wrong pumps, the wrong heat pump water heater. We had missing thermostatic balancing valves. So that system was really challenged. But through verification and, you know, support, those items were corrected. One issue is it was also designed for reverse return to have more balanced flow through the different banks of the individual heat pumps and the banks of heat pumps. This did not occur, so we didn't have as much balance flow as we would like. So the heat pumps are running kind of at different times, have different run times. And we'll kind of see over time how that affects it. The control strategy was the thermistors, and they were not installed properly initially. And so we had to reinstall them and make sure they were seated well in the thermal wells to make sure that the heat pumps were seeing the simultaneous call. So all of these things need to be verified. And so what this tells us, or what this tells me, is like we need ways to reduce some of these issues that were only identified through monitoring and M&V. We need simpler solutions. We need to make sure we have verification. So when we do install these systems, as we are installing more and more of them, we do see the performance in the higher 4 to 6 COP range versus lower range because things weren't addressed. Next slide, please. So I've talked about some like challenges and opportunities, right? But the thing I wanted to kind of close out with before I pass it back over to Meg to talk about production was really, we can look at some consumption reduction strategies or opportunities. And really this is all about thermal storage. And I know a lot of folks are thinking about this, investigating it, trying it out. And so we looked at it both in the individual as well as the central. So overall in the individual, we definitely want more volume. Definitely want to size the volume of the water heater and the set point to reduce potential resistance, because we want create as much warm water with a heat pump as possible. So for us, out of 8 experiments we did with 22 heat pumps, we found 140 with heat pump only mode kind of achieve that. But this was also because some of our experiments weren't as successful as we would like because of the proprietary mode configuration and logic in the reams. So we were doing a lot of testing with energy saver mode, which really ended up triggering a lot more electric resistance than we desired. And so that they were not as productive or as kind of successful as we kind of anticipated. So this was a limited set, but both this worked out well in winter and summer. We also found like load shifting in incremental stages is better. We could not test that. We did kind of at a single point in change time, we would change like a 20-degree change in the set point temperature, which is not the best mode, versus more of these AI kind of thermal load shifting that will do it incrementally. but definitely an opportunity there. We need to think about sizing to do that, and Emily will talk more about that. And just a brief touch on the central heat pump water heater system. When you have a lot more storage, so there's more opportunity. And really what we did in this study was a conservative proof of concept. All we did was turn off one heat pump and one bank. So we had 3 banks, 4 heat pumps to a bank in one of the wings of Sunnyvale project. And we turned off one of the heat pumps from 4 to 9. It was very conservative because we were shutting it down. We wanted to make sure we didn't negatively impact tenants. And that ended up being a 20% savings for that bank. But because we were turning off a heat pump that was dealing with really low load, it was a 4% overall savings for the plant. But what that tells us is there's a lot of opportunity here, and we need to do kind of more work and testing and provide more guidance on how to achieve thermal storage and load shifting in central systems, because that can also, as we look at achieving Z&E and meeting our goals, I think these strategies will be incredibly beneficial there.
Great.
So with that, I'm going to turn it over to Meg to talk about production.
Great, thanks, Amy. So just as there are sort of unforeseen challenges or maybe unforeseen loads on the consumption side, the same goes for the production side of just, different production, energy production outcomes than was modeled or predicted in the design phase. So you can go to the next slide, Emily. So here are a couple, there are kind of 2 main categories of discrepancies when looking at PV production or the PV component of zero net energy from the design phase to the operational phase. So one of the main sort of discrepancies between modeled and actual there is that the PV system does not perform as expected. It falls short of modeled annual energy production, and you don't see as much production to offset the building loads or the building consumption. The other sort of main category, which was a really interesting finding from monitoring at these properties, was that the PV credit within VNEM systems, that PV credits are not actually allocated to align with the different meters consumption for which those credits are allocated. So we have a pretty clear-cut example of how that can go wrong. So I'm going to first talk about how modeled production does not, or modeled actual production does not always live up to modeled production in 3 main categories of, natural discrepancy or naturally caused discrepancies, physical discrepancies, and utility side discrepancies. Next slide. There, year by year, there are variations in weather and natural events or disasters that can sort of overall reduce the solar access to a site or to a PV system. So this is what I've sort of categorized as naturally caused discrepancies. Some ways that solar access can be reduced are just by variations in weather year by year. You might have a more rainy year than is average, and therefore more cloud cover. There are also specific weather or natural events that might reduce solar access. We saw one that I'll talk about in a little bit this past September, when the sun was blocked out in the Bay Area just a couple days after the Creek fire started. Another is shading from tree growth. It's it's hard to plan for or anticipate how a tree will grow and where shading will be increased over time. So that's something that, shading's taken into account during the design phase, and a sun eye might capture how shading might change, but it doesn't always capture the whole picture. And then lastly, there's residue from either natural events like a fire event or agricultural events. If a system is installed near agricultural sites, there's a lot of dust in the air. And so you can see here, these are both photos from the PV system at Atascadero. On the left here, you can sort of see, it's kind of hard to see in this photo, but some residue sitting on the panels that depletes production. This photo was taken 10 days after the August 17th lightning event that caused thousands of wildfires to outbreak across the state. So you can see how ash has collected on the PV panel there. And then on the right here, you can see how a tree has sort of grown and is sitting, not only casting shade on the panel, but is physically touching the panels as well. Next slide. And so this chart really represents how variations in solar access over years can really change a system production, and how, you know, average annual weather data being used for modeling expected PV production is not always going to give you the whole picture. So this is PV production or energy production data from the PV system at Benner down in Sunnyvale, and each line represents a different year, so 2018, 2019, and 2020. I wanted to call out a few specific events just to show how, you know, weather events or just natural events can really have a dramatic impact on PV production. The kind of most alarming one, I guess, is on the left-hand side here. You can see the Creek Fire starts on, I believe it was September 5th, and then we had those couple of crazy days in the Bay Area where the sun got blocked out and the solar access was reduced to like almost nighttime or dusk levels, and you can really see how that plays out from a PV energy production perspective. Next slide. The next sort of production discrepancy can come from physical or installation issues, and there's just a wide variety, I don't want to say infinite, but potentially infinite number of things that can go wrong in installation and operation of a PV system on the physical end. And we saw that happen at the Cloverdale demonstration site. There was and we're not sure when this happened or how it happened, but essentially the half of the PV inverters that make up the VNM PV system were turned down to zero output. So that was sort of a physical issue that occurred, and we just in our monitoring practices through this study were able to see like something was not quite right with the PV system. It was outputting way less than expected. And in this graph, you can see this is net building consumption. So, you know, in these summer months in 2018, when this issue was occurring and in play, the net consumption of the building was positive. The building was consuming a lot more energy on a monthly basis than the PV system was producing, and therefore offsetting. And you can see in this called out month in February of 2019, that's when the issue was fixed. And once it was fixed, you can see the PV system is producing in full force, and that allowed the whole property to achieve net zero energy. And I think one of the main takeaways from particularly with the physical issues and some of the interconnection issues I'm going to talk about in a moment is that having a PV monitor or a third-party PV monitoring system is absolutely critical, and it's critical to not only have installed with the system, but to actively use it to catch some of these issues. Next slide. And lastly, on the production discrepancy end is there are sort of what I've called utility side issues. So with billing and interconnection issues, we saw one of these was another issue at the Cloverdale property where the solar credits were not appearing on the bills. So the PV system was interconnected in November 2017, and that PV system was operational and producing energy, sending it back to the grid to offset bills at the property from November until July. But that's not shown in the utility data because solar billing was not set up. Utilities have said that it can take up to 6 months for solar billing to be set up. So there is a bit of a lag or delay period. But in this particular instance, it was actually missed. And so there were 8 months for which production was happening and not showing up on bills. So once we saw this in the utility data, we were able to engage the utility, and solar billing was set up. And sort of another problem from this is that luckily the utility is willing to retroactively credit for all of the production that occurred back to when the system was turned on. But particularly in the affordable multifamily housing space, it's good to get those credits and bill credits and savings, but at the same time, residents and building owners have bills and expenses due now or in the present. And so missed credits, though they might be received later on, is still very problematic. And then next slide, I'll talk about allocation issues. So one of the
I just want to let you know we got about 2 minutes left, and you're doing a fantastic job. We got a couple minutes left.
Oh, okay. Thanks, Sean. I'll talk through this really quickly. But as I mentioned at the beginning, the VNM allocation can also be sort of a big determinant of meeting zero net energy, particularly from a cost standpoint. So here's an example from Atascadero, where the VNM allocation was very misaligned with the actual meter consumption on the common area meter. So you can see one building was able to meet Z&E, whereas the other building was not, and you can sort of see how that played out in reality. And from an aggregated energy consumption standpoint, you might still be able to meet zero net energy, but from a cost standpoint, those misallocation of credits will actually increase your costs, where you might have had a lower paying lower utility bills. So that's sort of a quick summary there, but I want to pass things off to Emily so she can touch on the modeling side of things.
Yeah, so I'll just go really quick through this so we end on time. What I was going to talk about is we had kind of two different ways of looking at the modeling side of things. One was from our initial Z&E sizing, and this is from Redwood Energy's perspective. We use different tools to come up with a Z&E estimate, but main takeaway here, no modeling tool is perfect, and there are loads that aren't represented in the software. So for example, skipping over to Atascadero, our estimated site consumption, we had to add in kind of like laundromat loads, miscellaneous loads to come up with a better estimate. And looking at Calistoga and Cloverdale, Meg talked about this a little bit. We used Calistoga's data to inform Cloverdale. So originally, our first estimates, we oversized the solar array, but it ended up, when adding in the new data, it was actually more just closely offsetting instead of oversizing the solar array. It was more closely matched to the predicted loads there. So that's Cloverdale again. And then another perspective, we looked a lot at the 2019 software, and feel free to email me if you have any questions about this kind of stuff. But we looked at total water use, and there's some discrepancies there between models. And yeah, since we were so focused on hot water, our domestic hot water systems, we looked at total water use, and we looked at the draw profiles pretty closely as well. And main takeaway, occupancy assumption in the software is lower than what we observed at our projects, because our projects are affordable housing and the algorithms are based on market rate housing. And I'll just skip over these to get to the end here. Yeah, so I'll send it back to Amy if you want to just make a brief conclusion statement.
Yeah, I think if folks can look at this later, just, we were finding different opportunities in each of these, from consumption to production to modeling, and really you know, overall, all electric Z&E is totally possible in multifamily housing. But as we look at kind of doing improvements and changes to scale this success across all projects, we really found recommendations that fall under like design and specifications in engineering, codes and standards, testing, verification, and operations and maintenance. So you can kind of look at these conclusions later. But I want to go to the next slide, Emily. Only to say kind of coming soon, near you, will be our final report, case studies, and technical briefs on this research project. So you guys know final reports for CEC, we'll have that, but then we're also pulling out deep dives into like the modeling that Emily just really breezed through in these last few minutes. Some of the stuff on thermal storage or PV that Meg was talking about, as well as just domestic hot water systems and crankcase heaters. So we'll have these technical briefs taking deeper dives into these topics that will be beneficial. And we'll have case studies on a couple of projects. So those will be coming soon in the next couple months. And so if you want to talk with us, we're happy to talk about it.
Well done. Fantastic research. There's a bunch of comments and questions over in the chat. Would y'all be willing to go over there and dig into them, please?
Yes.
And fantastic job. Proud to be associated with you.